Welcome to The Explainer. Today, we're unpacking a massive blind spot in how AI reads the news. A fascinating new paper submitted to Archive introduces a hierarchical neural architecture that finally teaches AI to look at the big picture. We're going to explore how evaluating a whole document instead of just isolated sentences is literally changing the game for natural language processing and media bias detection. So, to really understand why this new architecture is such a big deal, we kind of have to ask ourselves, how do human annotators actually read differently than AI? Well, think about it. If you read a sentence at the very end of an article that completely changes the context of the opening paragraph, your brain naturally connects those dots, right? You track that narrative flow. Baseline AI models, on the other hand, basically have amnesia between sentences. Okay, here's our roadmap for today. We'll hit 1. The context problem. 2. The HierBias architecture. 3. How document context works. 4. Benchmarking BABE and BASIL. And finally, 5. A developer implementation guide. Let's get into it. Starting off with Section 1, the context problem. The gap between humans and machines here is honestly staggering. Standard AI baselines treat every single sentence as an isolated, completely independent token stream. It's kind of like trying to understand the plot of a deeply complex movie just by looking at random shuffled screenshots. Human annotators naturally track narrative flow, contradictions, and framing across paragraphs. If sentence B modifies or flat out contradicts sentence A, standard machine learning models simply throw that vital relationship away. But humans, we rely on it to detect nuanced things like editorial spin or political framing. Moving right along to Section 2, the HierBias architecture. Let's see how they fix this. This pipeline elegantly replaces that isolated sentence classification. And get this, it does it entirely without needing any manual feature engineering, which is a massive win for developers. It's a clean 3-step process. In Step 1, a sentence-level Roberta encoder processes each sentence independently to pull out local semantic representations. Then, Step 2 introduces a cross-sentence transformer aggregator. This aggregator pools those representations across the entire document span, using attention mechanisms to weigh how earlier sentences condition later ones. Finally, Step 3 feeds all that aggregated context right into dual output heads. Now, the magic really happens with how these dual heads use those aggregated context vectors. First, you have a binary head that spits out a straightforward bias or no bias probability. But right alongside it, there's a 4-class head that maps that exact same context to specific fine-grained bias typologies. By forcing the model to solve 2 problems at once, detecting the presence of bias and classifying the specific type, it builds this incredibly holistic understanding of the text. It literally forces the model to pay heavy attention to inter-sentence dependencies rather than just processing each sentence in a vacuum. All right, let's shift gears from the architecture to the underlying math in Section 3, how document context works. The researchers formalized something they call the context-conditioned bias probability. The math is dense, but the concept is profound. They theoretically proved that leveraging document context strictly reduces the Bayes error. And if you're unfamiliar, Bayes error is basically the absolute mathematical floor, the lowest possible error rate any model could ever achieve. They proved you can lower that floor as long as sentences share information. In practical terms, this means if one sentence modifies or qualifies another anywhere in the text, the model now mathematically weights that connection, inherently making it more accurate than a model just guessing sentence by sentence. Plus, this approach introduces a multitask generalization bound. By jointly training the binary detection head and the type classification head, the model learns bias-agnostic linguistic features. This is a huge deal, folks. Human annotated bias data is incredibly expensive and rare. So a model that squeezes more signal out of every single training example, that's a massive cost saver for AI labs. Because it extracts so much more context, it prevents overfitting on sparse data splits and actually stabilizes gradient updates during the fine-tuning process. Next up, let's look at the empirical performance in Section 4, benchmarking BABE and BASIL. BABE focuses on political media framing, while BASIL covers broader editorial bias. The results here are wild. We see a massive 4.3% jump in the Matthews correlation coefficient over the current state-of-the-art bias detector. That is a truly significant leap forward in AI news models and baseline NLP accuracy. Let's break down where that number comes from. Looking at the breakdown, HierBias achieves an F1 score of 0.853, which is a solid 2.6% improvement, and the MCC reaches 0.723, giving us that critical 4.3% jump. What's crazy here is that these gains hold across both the BABE and BASIL annotation schemas, without even needing to retrain the Roberta encoder. The model relies entirely on that cross-sentence aggregator to successfully reweight the contextual signals for both domains. I want to pause for a second on why that specific MCC metric is so absolutely vital. F1 scores are great, sure, but they can easily mask severe class imbalances in your data. The Matthews correlation coefficient, on the other hand, rigorously penalizes class imbalance. It ensures you have balanced precision and recall across both bias and non-bias classes. And that's why this 4.3% MCC jump matters so much for production workflows. It drastically reduces false positives. In real-world editorial pipelines, overflagging just triggers unnecessary, highly expensive human review. HierBias avoids that trap entirely. We also know for sure this isn't just a statistical fluke. The improvements are mathematically validated, with statistical significance confirmed via McNar's test at a p-value of less than 0.05. McNar's test is pretty much the statistical gold standard for proving that a new machine learning model is actually smarter and not just getting lucky on a few guesses. Ablation studies also mathematically confirmed that the cross-sentence aggregator and the dual-head training each independently contribute to this performance lift. Finally, let's wrap up with Section 5, Developer Implementation Guide. If you're a machine learning engineer looking to build this, listen up. Because there isn't a public code repository for this archive paper just yet, you should treat this as a solid research baseline. You'll need to manage your context window constraints carefully. If you're processing long articles, definitely use chunking or sliding windows to stay within Roberta's 512 token limits. Also, we all know the visceral pain of a sudden CUDA out-of-memory error right at the end of an epoch, right? Keep a close eye on that VRAM overhead during multitask training. Monitor the gradient flows so the dual heads don't interfere with each other. Make sure you map your target taxonomy correctly to the 4-class output space. And for the love of reproducibility, paint your PyTorch and Hugging Face Transformers versions. When building your own pipeline, remember that good evaluation hygiene is really what separates a neat research experiment from a production-ready AI. You absolutely must report both F1 and MCC to accurately expose precision and recall trade-offs. Run McNamar's test against your current baselines before claiming victory, and crucially, log your calibration curves to verify that your context-conditioned probability outputs remain well-calibrated across varying document lengths. If you're an engineer or researcher looking to dig deeper into the theoretical bounds, the multitask metrics, or the exact annotation guidelines, you can jump straight into the source material on arXiv under the identifier 2606.26100. As we wrap up this explainer, I'll leave you with this thought. The era of AI analyzing isolated sentences is ending. Given the massive efficiency leaps and accuracy gains we've seen today on datasets like BABE and BASIL, how will shifting toward context-aware models redefine the limits of your own AI pipelines? Keep questioning the baselines and keep pushing the boundaries.